What's up, you guys? How are y'all doing? So, I've been in here teaching my rear end off to you guys, just working my tail away, making a video for you. And all of a sudden, I see there's no video. That's so sad. So, the camera fell over. I don't know what happened. The camera fell over, the ring light fell over, like everything took a dive. And now it's telling me I have no video. Look at all this I've been working with you with. Man, I was going to town, you guys. We were just about to close. You know my video is only like 28 minutes or so. And I don't know what happened, man. I don't know what happened. I hope you guys can see pretty well. Let me see. Let me check the lighting. Let me add some lighting to it. Let me see what I can do. If I can add some lighting to it. I had my fancy little ring light right here. Just like that. You see it? But no. No. All of a sudden, it just fell over. I am so frustrated. Sort of. Can you guys see? Is that helping? Oh, no. Does that help any? All right. Let me try to set you up with some light, you guys, so I can see what's going on. I don't know if that helps or not. What do you think? Maybe? Maybe. We'll see. So, wow, my hair was, look, hair's almost falling down because I've been going to town. So crazy. Okay, let me not dwell on it. Oh my gosh, I don't even know where to begin, you guys. I don't even know where to begin. Like, I have so much stuff going on. I said so many things to you. So, hi. This is, and to top it off, you all, my masses. I gotta say masses because it's not all guys. To my masses out here. This is probably the third or fourth video I started. Because the first one, I didn't have my SD card. And then the second one, I don't know. This is like the third video. This is so crazy. Nonetheless, hi, I missed you all. Thanks for viewing. Welcome back. Welcome back. So I went over word problems a minute ago before I got here to linear equations in one variable. So I guess I'll just have to backtrack. But I didn't want to erase everything I'd already done. Okay? What I had stressed to you before was that these are words for mathematical operations, all right? Operation words, product implies multiplication, and these are the common multiplication symbols. The dot, the parentheses, yes, parentheses has like 2 or 3 jobs, you know. I was gonna make a joke, but you gotta watch out. You gotta be culturally responsive these days, right? So, parentheses have a lot of jobs. And another way to show representation for multiplication is with the X. When you see the word quotient, it implies division, and so you know that's the division symbol, or the fraction bar. And yes, anytime you see quotient, you should know, ooh, I'm probably going to make a fraction. That is correct. Sum, I had even done funny stuff. I'm like, oh yeah, that means sum, this means sum, this means sum. But it's just not as funny now. So right now, you just have to worry about that. Difference is going to be subtraction. I've also posted words, and I think we went over these on vocabulary when I first gave you the vocabulary. I'm sorry, I know I see them defeated. I was so pumped, you guys. And the camera just took a dump. Oh my God, I'm so mad. But it's okay. Learn these words, look these words up, write them down, be attentive to it, okay? You're gonna see these words throughout the rest of your math, so you kind of have to know what it means ASAP. God, I don't even know where to start. I thought I had finished with word problems and moved you over to linear equations in one variable. So we were talking about this algebraic expression right here. This is called an algebraic expression, of course, because it's got variables in it. Your algebraic expression has 3 terms. One term, the positive 3x squared, positive 4x, and negative 5. I've broken them down right here. These two, your 3x squared and your 4x, those are going to be your variable terms because they have a variable in there, of course. So anytime there's a letter there, that's a variable term. Your -5 is called a constant because it's going to give you that consistent value. The value of -5 is not ever going to change. These values will change depending on what x does, because if x is 1 right here, then that's 4. But if x is 2, then that's 8. If x is 3, then that's 12, and so forth. So these are variable terms, right? It's going to vary depending on what value the letter represents. But again, this -5, just constant. It's not being multiplied by anything. Nothing's happening to it, so it's just going to be -5, right? It's called a constant. And so I was saying that there's 2 parts to your variable terms. 3 is the coefficient. So all of the numerical values in front of your variable terms, those are going to be your coefficients. Those are going to be your leading coefficients. So your coefficient here is what? 4, yes. 4 is your coefficient there. And so I was saying that your variable term has 2 parts. It has the coefficient, and then it has the variable part, okay? And in this case, 2 is the exponent to that variable part. Right here, I was talking about how you haven't reached the 1. So don't worry about this. We'll come back to that part. I was just reminding you that even if you have, when you have a fraction and the numerator is smaller than the denominator, no matter how many numbers are in that denominator, no matter how big your denominator is, if your numerator is smaller than that denominator, then you're not even at 1 yet. So like get a ruler out and look, or a tape measure or something, or Google it real quick and look at it. From where it goes 0 to 1, you're not even at 1 yet if your numerator is smaller than your denominator. But I think I was talking about over here, I believe I put that was up there because I was telling you about coefficients, right? Because we were moving to like terms. So like terms are when you have variable terms, but they have the same variable part, and that variable part has the same exponents. So that's where we were when my camera took a dive. We were almost done for the day, you guys. That was so sad. But over here, I was using these as an example. So variable terms have the same variable part, and the variable part has the same exponent. 3x, 1/2 x, and 10.398x. All of these would be like terms because they all have the same variable part. Your coefficients can be different. It's okay that the coefficients are different. It's okay that the coefficients are in different forms. This is whole number, this is fraction, this is decimal. All of that is okay as long as they both have the same variable part. Now if you had which of those would be like terms? Remember, like terms have to have the same variable part, and that variable part has to have the same exponent. So which of these would be like terms? The coefficients can be different. It doesn't matter what the coefficients look like. But if you said this one and this one are like terms, you are correct because they have the same variable part, which is an x, and the exponent on the x is a 2. So they have the same variable part, the same exponent, they are like terms. It does not matter if they are not. Look, this is a like term as well. This one, and this one. I'm going to circle that one in brown too because it's a like term. All 3 of these are like terms. They have the same variable part. The variable part has the same exponent. We don't care about the coefficients. The coefficients don't have to be the same for them to be like terms. All right? I've explained the board that you see. Oh man, do I go back? Do I go back, you guys? Probably so. Let me go back, all right? Save this thought. Save this. Get a good picture of it. You got it, right? You can screenshot it. You can pause it. You can go back to it. You'll have to remind me of it. We did this part, but now in all due conscience, because the camera fell out and knocked the SIM card out, I have to redo what I did because I cannot, in my right mind, keep moving without knowing that for sure, positively, we have finished covering word problems. So I'm going to flip back real quick. I want to give you a couple examples with these word problems to help you recognize when to do what. Let's start with this. A number increased by 9. A number increased by 9. Could barely see that, huh? And then we have 9. Decreased. Oh my gosh. Spelling is just horrible, huh? That's why I do math. All right. I feel so bad. I was so pumped and motivated. I had all this written on the board. I had everything already there ready for you. It's okay. It's all right. So here's 2 examples I want you to be attentive to. A number increased by 9. 9 decreased by a number. Man, I went so hard on expressions and equations. I'm sorry. Okay, let me stop. Notice that this is just a phrase. It is not a complete sentence. 9 decreased by a number increased by 9. How do we know how to write this mathematically? Usually, what comes first is what you write first. A number, we don't know what the number is, and I told you today we're going to let n equal a number. I chose n because my name is Nikki. A number increased by 9. A number increased by 9. No equals needed, no nothing, because it's just an expression. It is not an equation. It doesn't say is, it doesn't say results in or leads to, anything like that. It just says a number increased by 9. 9 decreased by a number. 9 decreased by a number. Just like that. Don't overcomplicate it. It is just what it says. All right? That's for your expressions. I know that they seem a little self-explanatory sometimes. Sometimes they don't. It takes a minute to break it down. Once you learn the rules and you realize it's consistent, you'll be fine. Right? And a couple other examples I had given you. I'm just like, man, I was so ready for y'all. That's all I'm saying. I was very excited. 20 minus quotient of 7 and a number. All right. How would we write this? Give it a try. I'm going to let you write it first. We know minus means that symbol. Quotient, we're going to have a fraction. So we have 20 minus quotient of 7 and a number. So we know quotient of tells us, oh, this is what we're getting ready to divide. 7 and a number. We're dividing 7 and a number. Now, if it was a number and 7, then the n would be on top. It would be the numerator. But this time, it's 7 and a number, so we know that goes right there, and it's 20 minus that. So 20 minus 20 minus the quotient of 7 and a number, right? The other one I wanted to show you is quotient of, yes, we're dividing again. We are 7 and sum of a number and 8. All right, quotient of 7 and sum of a number is 8. So we want the quotient of 7 and, did I write that right? Quotient of 7 and sum of a number in 8. Yep. You do it like this. I need that and right here because that's going to tell me what's being divided, what's not being divided, where to break it up at. The quotient of 7 and sum of a number in 8. So now I know, and there was an and sign there, but you know my math brain knows the words better. So quotient of 7 and sum of a number in 8. A number and 8 being summed. That is, notice again that this is an expression. We have no equals up here other than the key. Okay? We don't have any equals up here. You cannot just throw an equals around like that. Equals means is. That's what this equality, remember equation, equality. You cannot throw it around loosely like that. All right. Was there another one I showed you in here? I think that was it. Throw some stuff up in the chat, in the comments, if you have any questions, if you feel like there's anything I skipped. Throw it in the chat for me, and I'll answer you. Okay? So back to where we were. Like terms. Okay. I want to give you a few more examples. Go back to the like terms. I'm so disappointed, you guys. You all, my masses. So disappointed, masses. It was so great. So great. I can't believe it knocked everything off. The camera fell over, and then it says, no, nothing to preview. I was like, what do you mean, nothing to preview? Nothing to preview. Okay, so we were talking about like terms. Oh, I wanted to, because we're moving to simplifying. We're going to do linear equations of one variable. Back to what I had. One variable, one, and I love math, you guys. You all, my maths, my basses. Look, root word of variable is vary, root word of equations is equal, root word of linear is line. Like they mean what they say. Love math, love math. Okay, so we went over like terms. So now we're going to work on combining like terms. We identified what like terms are. All right, are these like terms? Are those like terms? No. No, they are not. They have the same coefficient, yay. The variable part has the same exponent, but the variable parts are not the same. So no, are not like terms. What about this one? I was like, I just saw a good one. Are those like terms? Yes. What if, let me ask you this. What if it said, would they be like terms then? Look carefully. Do they have the same variable parts? Now the variable parts are not in order, but there's a special thing, a special property about multiplication that says that they don't have to be in order, right? a commutative? Is it commutative or is it associative? I'll let you look that up. But basically that says 5 times 4 times 9 is the same as 9 times 5 times 4. It's the same as 4 times 9 times 5. It's the same, you know, no matter how you multiply it, you're going to get the same product. So with multiplication, that's why I say don't do no work. You got to save all these rules in your head. With multiplication, it doesn't matter what order you multiply. They're the same. So here, yes, they are like terms. The variable parts are the same, and the exponent is attached to the same variable. So those are like terms. Yes, they are. Yes, like terms. So let's work on combining like terms. You ready for that? I'll show you how to combine like terms. To combine like terms, you are simply adding and subtracting. That is it. You're adding and subtracting just like normal, except for now you have, right? We have variable terms to use. So, an example says, what if we had 22y squared? Where'd it go? Uh-oh. Plus 10y minus 30y squared. Again, we're not just going to go throw an equals up there. They didn't give us an equals because this is an expression, not an equation. So we simplify vertically. These two I know are like terms, right? Because they both have a y. Let's see. They all three have a y, but this one doesn't have a y squared, right? So I'm just going to take these two. I'm going to take my two like terms, which is going to be this one and this one. Yep, that negative go with it. The sign always goes in front of the value. So a positive 22 and a negative 30. What's the rule? If my signs are different when I'm adding and subtracting, if my signs are different, I subtract my values and take the answer gets the sign of the largest number. This is a positive 22. This is a negative 30. My signs are different. This one's positive, this one's negative. I'm going to subtract. 30 minus 22 is what? 8. Yes, that's what your fingers are for. Use them. It is 8, and because 30 is the bigger number, 30 is bigger than 22, and it's negative, my answers will be negative 8. Keep that y squared, 10y. So see how I just bring it down? I didn't throw an equals up there. I'm not just going to throw an equals. Final answer right there. Negative 8y plus 10. Negative 8y squared plus 10y. Well, what about over here? Let's try another one. If we had negative 11q plus 17 minus 4q minus 3. In this situation, we know that our constant values are always like terms. So this is my constant value, positive 17, negative 3. Those are my constant values. Those are always going to be like terms. And now look, these two just have a q. My q is to the first power on both. So I know these two are also like terms, right? So now I will combine my like terms. Combining like terms is simply adding and subtracting. So let me write that there. Basically, adding and subtracting. So you definitely have to know your rules for adding and subtracting integers to combine like terms. Okay? My signs are the same. I have a negative 11Q and a negative 4Q. When my signs are the same, I will add my values and keep the sign. 11 and 4 is 15. And then my constant values, they are opposite signs. My signs are opposite, they're different. I will subtract and keep the sign of the biggest number. Here, my biggest number is 17. 17 minus 3. Right? Okay. That's a little bit, I'm still really disappointed, but that's okay, you guys. My masses, not you guys, my masses. All right. Oh, there's another word you all need to make sure you know. Distribute or distribution. That is a form of multiplication. And we're about to move into distribution, so I want to make sure that everyone already knows about distribution and what it is. Okay? That means, and it's a distributive property. You should have looked it up or already come across it before, but just in case, I'm going to add that to your vocabulary list and tell you how you have to know what it means. And you do. Okay? Again, it means to what does it mean to distribute? It means to give out, right? If you were distributing flyers, that means you'd be passing out flyers to everybody. And so that's what distribute means, to give to everybody. You often come up to that situation because you'll have parentheses, you'll have values inside some parentheses that you would have to distribute to. So for instance, let's say we have 2, and this would be times 6y minus 3z. Okay, so we're going to simplify this expression. Oh, I see a better one, but let's go ahead and do this one. So to distribute, like I said, is to give to everybody in there. I told you that parentheses also represent multiplication. So yes, you're going to multiply this 2 times everything inside the parentheses. But this is also where your order of operation comes into play, because if you're following your order of operations, you would combine all like terms inside your parentheses first. Okay? And then you would distribute. So you have to combine all like terms. For us, we see these are not like terms. This is a Y, this is a Z. If it is not like terms, you cannot combine it. You cannot combine it if they are not like terms, that 360. Cannot combine it if they are not like terms. But here, we'll distribute. Again, that's multiplication. 2 times 6, get your multiplication tables out. Use your fingers, no calculators. 2 times 6 is 12, and that y doesn't go away. You can't just make things fall off either. Things don't fall off, they don't disappear. You are mathematically handling them, and we'll talk about what happens, okay? And this 2 times negative 3x. It sounds like I heard it